Welcome to the Explainer. Today we're cracking the code on one of the most powerful tools in all of math and physics, vectors. And we're going to see how one simple, almost intuitive trick can solve problems that seem impossibly complex. All right, let's just jump right in with a problem that sounds, well, impossible. Picture this. You're an engineer designing a spacecraft. You've got dozens of thrusters, right? And they're all firing with different amounts of force in all sorts of different directions, sometimes all at once. So how in the world do you add all that up to figure out where your ship is actually going? Or, hey, something a little closer to home. An airplane trying to land in a heavy crosswind. How do you predict its actual path? It's a mess, right? Well, the solution is surprisingly simple. And it all comes down to shadows. No, seriously, the secret to adding up all those chaotic, complicated forces is just to look at the shadows they cast. Okay, but before we can even think about casting shadows, we've got to map out the world these forces actually live in. And spoiler alert, it's not a flat, two-dimensional piece of paper. I mean, life happens in 3D, right? So we need a 3D map. We start with the basics you remember from school, the flat x-axis for left and right, and the y-axis for up and down. But then we add a third axis, the z-axis, that comes straight out at you. It's perpendicular to the other two. And boom, that gives us this three-dimensional space, mathematicians call it R3, where any point, any location can be nailed down with just three numbers. It's x, it's y, and its z coordinate. So, to make sure we're all looking at this 3D world the same way, there's this super handy trick called the right-hand rule. Seriously, do it with me right now. Take your right hand, point your fingers straight out along that positive x-axis. Now curl them like you're trying to grab the positive y-axis. Where's your thumb pointing? Straight up, right? That's it. That's your positive z-axis. It's the standard everyone uses, so we're all on the same page. All right, so we've got our 3D map set up. Now it's time to introduce the main character of this whole story, the vector. So what is a vector? It's basically just an arrow floating in space. That's it. But this arrow tells you two super important things. First, how long it is. That's its magnitude, which you can think of as its strength or its power. And second, which way it's pointing. That's its direction. So things like force or speed, or even just moving from one place to another. Yep, those are all vectors. Okay, and here's where it gets really cool. Every vector kind of has two secret identities. They're both the same thing, just described differently. The first one, the polar form, is how we've been talking about it so far. You just state its total length and what angle it's pointing at. Simple enough. But there's this other way, a much more powerful way, called the component form. And this way describes the vector by breaking it down into its individual pieces along each of those axes we just talked about, the x, the y, and the z. And this component form, this is our secret weapon. This is how we're going to tame all that complexity we started with. And how do we find it? You guessed it, by breaking the vector down into its simplest parts, its shadows. Let's make this crystal clear. I want you to imagine our vector is a real physical stick, okay? And you're holding it at some weird angle in the middle of a room. Now, take a flashlight and shine it straight down from the ceiling right over the stick. The shadow that stick casts on the floor, that's the first piece of our puzzle. That shadow right there on the floor, that's the x component. It's literally telling you how much of that stick's total length is pointing in the x direction. And the way we find its length is with the cosine function. Now, don't let the name scare you. Cosine is just like a chopping function. Its whole job is to take the full length of the vector, the stick, and chop it down to tell you the length of the shadow that's adjacent, or right next to, the angle you're working with. Okay, now what happens if we move our flashlight? Let's shine it from the side so the stick casts a shadow on the wall. Well, that shadow on the wall, that's your y component. It's the part of the vector that's working in the up and down direction. And to find this one, we use sine. Sine is just the other chopping function, the one that finds the shadow opposite the angle. So see the pattern? Cosine for the shadow next to the angle, sine for the shadow opposite the angle. That's really it. Simple as that. All right, so I can hear you thinking, why are we doing all this? Breaking things into shadows, using sine and cosine. What's the big deal? What's the payoff here? The payoff is everything. Because what components do is they take a really messy geometry problem, full of weird angles and lines, and they turn it into simple, clean arithmetic. That's it. You're basically taking a tangled knot of yarn and neatly separating it into individual straight threads. I mean, just look at this. If you want to add two vectors together, or 10 or 100, you can just throw away your protractor. You don't need it anymore. All you do is add up all the x pieces to get your final x piece. Then add up all the y pieces, and finally add up all the z pieces. It's just simple addition right down the columns. It's almost like a magic trick. And that brings us right back to our crazy spacecraft problem. See how we solve it now? You take the force from every single thruster, you break each one down into its x, y, and z shadows, and then you just add up the columns. The final numbers you get are the components of the one single vector, the resultant vector, that tells you exactly where the ship is going and with how much total force. All that chaos just clicks into place. It becomes perfectly orderly. But look, this isn't just for rocket science. Not at all. This whole idea of taking something complicated and breaking it down into its basic building blocks, it's like a master key, a key that unlocks problems in all sorts of different fields. Seriously, once you see it, you start seeing it everywhere. Your GPS, it's just breaking your trip down into north, south, and east-west vector components. An engineer designing a skyscraper, they're breaking down the force of the wind into components to make sure the building stays standing. That awesome jump your character makes in a video game, that's just a velocity vector split into its horizontal and vertical components. It even goes into data science, where something as complex as human behavior can be broken down into vector components, like spending habits and brand loyalty, all to predict what you might do next. And that leaves us with a really powerful final thought. Because this isn't just a math trick, is it? It's a whole way of thinking. It's a method for looking at a problem that feels overwhelming, totally chaotic, and finding a way to make it simple and manageable just by breaking it down. So it makes you wonder, right? What other huge, complex problems out there, in science, in our lives, in the world, could we finally solve if we just got better at finding their simplest component parts?